There we go. Okay. So today we are shifting into 11.2, which is sector area and arc length. So if you think back to our vocab that we talked about on Monday, we talked about sector, which is just like a slice of a circle. If you think about a circle as being a pie or a pizza or something like that, it would be like a slice of pie or a slice of pizza. That's considered a sector. And then arc length is just a portion of the circumference. And it's all defined by these things called central angles. So we're going to take a look at how we would solve for things like sector area and arc length today. So go ahead and grab your notes and we'll get started. Okay. So to get everything started for today, 11.2 sector area and arc length. Okay. So let's start with arc length first. We talked a little bit in our vocab section in 10.1 about what arc length is. And we define it as a portion of a circumference defined by, excuse me, allergy season starting, a central angle. And when we had kind of a picture of it going, if this is our circle, and this is a central angle of the circle, the arc length is the length of just this part of the circle. So it's a portion of the entire circumference. Okay, so how do we find exactly what portion that is of the entire circumference? Well, there's a formula we can use. Or you can also solve it using proportions. So we'll kind of take a look at both of those. So the first way. Formula. We know the arc length. If this central angle is theta, and this distance here is the radius, theta over 360, and if the whole way across is diameter, times pi times diameter. Okay, so the reason it's theta over 360 is because if this is my angle, this is a portion of an entire 360-degree circle. So this is kind of telling me what fraction of my circle are we working with here. And then pi times diameter, we might recognize that as circumference. So we're just taking the circumference and multiplying it by what fraction of the circle we're working with here. So that is one way that you can find arc length. The other way that you can find arc length is using proportions. And it is going to look very similar to this. It's going to be theta over 360. And this is going to look very similar to the way that we saw things in chapter 8 with similarity. It's going to look similar to similarity. Theta over 360 is equal to the arc length over the circumference. And so the formula is basically a rearranged version of the proportion. So a better, I guess, representation of this might be the angle over 360 is equal to the arc length, we'll call that x as a distance here, over pi times diameter. So this here is just a rearranged version of the proportion method of solving this. It's the same kind of thing. Whatever works for you the best is the way that you should do it. I tend to prefer the formula version because, I don't know, I think of it better as this is a fraction of my whole thing. But whichever way works best for you to think of it is how you should do it. So with that, that's kind of the backstory to arc length. Let's actually find some arc lengths. And usually when you're going to solve for arc length, you're given information like the diameter and the central angle and stuff like that, or the radius and the central angle. But you'll also see problems where we're given the arc length and we need to solve for something like the central angle, or we're given, the arc length and the angle, and we need to solve for the radius and stuff like that. So with that, first example. We are, let's see, given this circle here. We'll call it circle A. And we're going to be given some information here. Measure of angle BAC is 65 degrees. And the length of DC is 10 centimeters. And we want to find the measure of the arc here. Give everyone a moment to write. Okay. Also, real quick, there's some arc notation that we want to take a look at together. So if we're looking at, actually, I'm going to pull off to the side here and talk about arc notation because I forgot we needed to mention that before we start talking about arc length. Arc notation. Okay, so if I have a circle here, bear with me for a moment with the colors. We'll call this and we'll have some other point over here. Okay, so if I'm going to label an arc, there's two different kinds of arcs. There's major arcs and there's minor arcs. And there's semicircles, but so a major arc, minor arc. So a minor arc is an arc that is less than 180 degrees. So like BC here, this would be a minor arc. And the way that you label an arc is you take the letters and you put a little curved arc thing over it. A major arc is greater than 180 degrees. So like this out here would be a major arc. And that's labeled with 3 letters to tell you that you're going to go all the way around the outside instead of just grabbing the minor arc here. So BDC would be how you would label a major arc. Okay. And then there's also semicircles, which is a half circle. And that would be 180 degrees. So like, let's say we had something like this, where this is a diameter. A semicircle would be like EBC. And you also label those with 3 letters. So a major arc is greater than 180 degrees. A minor arc is less than 180 degrees, and a semicircle is equal to 180 degrees. Okay. So sorry about that. Got a little bit ahead of myself. Skipped a section of my notes. Okay. So on our first example, if I have this information here, we have the measure of this angle, we have the measure of the diameter here, then I might have instructions like find measure or length of arc BC. So arc BC is the minor arc right here. And if I want to find the measure of that arc, here we go. We know that we're going to label our picture first. BAC, this angle right here, is 65 degrees. DC, this whole distance here, is 10 centimeters. So this is the diameter. This is our central angle. If I'm going to use the formula way, we know we have theta over 360 times pi times diameter. So in this case, our angle, theta, is that 65 degrees. It's that central angle. So I'm going to go 65 over 360. And that's the fraction of the circle that I'm working with here. And then we go times pi times the diameter. And in this case, the diameter that we were given is 10. Okay, so then I would want to basically type this thing here into the calculator. So that's what we're going to do. I'm going to open up a window of Desmos for it. Actually, we already have a window open. And make the font a little bit bigger here for us. Okay, so typing this in, we had 65 over 360. And then times pi times 10. That gives us 5.67 approximately. If you type it in just like that, that's what you'll get. Okay. So if you like doing it the formula way, that's how we would do it. Or we could do it the proportions way. So the proportion way is we have theta over 360 equals our arc length x over pi times diameter. So I would start plugging in the things that I have, just like we did in the formula way of doing things. So theta over 360 is still 65 over 360. And then we have x, because that's what we're trying to solve for here, over pi times diameter, so pi times 10. And then if I'm solving this the proportion way, one way that you could do it is you could multiply by 10 pi on both sides, and you would get the same kind of idea that we have up here. Or you could cross multiply to solve it. We could go 65 times 10 pi equals 360x. And then we would divide by 360 on both sides. And this is what we would type into the calculator. Either way, we should get the same thing. So let's try it. We're going to type in 65 times 10 pi divided by 360. And we do. We still get 5.67. So either way you do it is fine. This is just these are rearrangements of each other. All right. So either way, we should get 5.67 centimeters. Okay. So I've shown two ways. We have the formula method and the proportion method. Just curious, based off of your first reaction to it, we'll call the first way is the formula way, the second way is the proportions. What one do you prefer so far? What are we thinking? Or no preference? We out there? We awake this morning? What are we feeling? Or any questions about either of these? Any numbers we're not sure where they came from or anything like that? Okay. So any preference, formula way, proportion way, what are we feeling? Got to vote for the formula method? Anyone else? Formula. Yeah, I'm inclined to agree. The formula way is typically shorter, and it's just a rearrangement of the proportions. So most of what I'll show from now on is probably going to be the formula way. If you prefer proportions, though, feel free to continue doing proportions. Okay, let's do another one. Let's go. Here's our circle. P, Q, S, T. And this time we are told that measure of angle, call that O, POQ is 92 degrees. QT is 12 inches, or 1 foot. And we want to find the measure of arc PSQ this time. PSQ. Okay, so first thing we want to do, label our picture here. I know that POQ is 92 degrees. I know that this distance here is 12 inches. And I am looking for the arc PSQ. Is that going to be this small arc? Is it going to be the minor arc or the major arc that I'm looking for here? Minor arc or major arc? Yeah, this time we're looking for the major arc because we've got 3 letters involved. We know that. We also know that if I trace from P to around the circle to S to Q, we're looking for the larger arc here. Okay. So if we're looking for this measure, and I only know this central angle here, how could I find the angle for my arc? What could I do? Any ideas? Well, what's the degrees in a whole circle? 360. So if I take 360 and subtract away the smaller arc, or the smaller central angle, 360 minus 92, we get 268. And that would be the measure of my other angle, 268 degrees. So this is going to be theta in our formula. So my arc length is going to be theta over 360 times pi times diameter. So in this case, that's 268 over 360, because that's the fraction of the circle that I'm working with here, times pi times the diameter. QT was the diameter, 12 inches. So this is what I would type into my calculator. So let's take a look at our calculator. We want this time 268 over 360. That's the fraction of our circle. And then times the whole circumference, pi times diameter. So for this one, for our arc length, we get 28.06 inches. So this is 28.06 inches if we round to the nearest hundredth. Okay, one more example, and then it's your turn to give it a try. This time, we're going to be given something else. We're going to be given an arc length. But first, we're going to be given a picture. So, A, M, C, N. All right, so this time we are told that the measure of arc AC is 14.2 feet. And then we are also told that AN is, well, not 14. We'll do, let's see. So let's go 13 feet. And we want to find measure of angle AMC. Measure of angle AMC. So this time we're given different information. We have an arc length, we have the diameter, but we're looking for that central angle. So we're still going to use that same formula, theta over 360. and then times pi times diameter, but that's equal to our arc length. So this time, we know that this length here is 14.2. We know that this distance, the diameter, is 13, and we're looking for the angle theta, which is the measure of angle AMC. You do want to pay attention to which angle you are being asked for here. But anyway, let's plug in what we have. 14.2 is going to go in for arc AC. 13 is going to go in for diameter, and we're solving for theta this time. So we have 14.2 equals theta over 360 times pi times 13. And we want to get theta by itself. So this sort of thing is more of an exercise in algebra. Here we go. Let's start by getting rid of the fraction. So I'm going to multiply by 360 on both sides. And in my calculator, 360 times 14.2 gives me 5,112. And over here, we're left with theta times pi times 13. Then my last step, divide by pi and 13. Now, if you're using a regular calculator, you want to make sure that you keep these in parentheses. If you're using a Desmos, it doesn't matter as much because you'll be able to see the grouping more clearly. So in our calculator, this is what we're putting. 5,112 divided by pi times 13. And we get 125.17 is what it rounds to. Okay, so this is what we type in. 125.17 degrees equals theta. And that is our answer. Okay. So now it's your guys' turn to try. First, here's your picture. We'll say this angle is 49 degrees. And TC is 18 centimeters. Find the measure of arc BC. And then for your second one, we'll say measure of arc QS is 5 feet. We'll say that SP is, we'll go with 10.4 feet. Find the measure of angle QTS. Okay, so this one is like our first example. This one is like our third example. Go ahead, give those both a try. I'll give you little hints along the way if you get stuck. When you think you've got them both, put "got it" in the chat. If you started off with the equation, measure of angle BC equals theta over 360 times pi times diameter, you're on the right track. And we should be plugging in 49 degrees for theta and 18 centimeters for the diameter. So you're on the right track if this is what you type into your calculator. And then if you got approximately 7.7 centimeters, you are correct. 7.7 centimeters. All right, so the second one, we should start off with that equation. Measure of arc QS equals theta over 360 times pi times diameter. So it's the same equation idea, just plugging in things in different places. So plugging in 5 feet for the measure of arc QS, plugging in 10.4 for the diameter. And then we're solving this equation just like we solved the one up here. All right, and then your last step, if you're still checking work here, pi times 10.4 divided on both sides. So into your calculator, 1,800 divided by pi times 10.4. I would make sure to keep that in parentheses, just like on the last one. So we should get 55.09 degrees if you did it correctly. So looking at both of these, any questions, any numbers we're not sure where they came from, any steps we're not sure how they happen? Okay. So with our last little bit of class here, we're going to talk about sector area here, which goes pretty much the same as arc length, except we're using area instead of circumference in our formula. So here we go, sector area real quick. So we also have the formula or the rearranged proportion way if we would like. So we've got the formula, and it's going to look very similar to the arc length one. It's still theta over 360. And then this time, though, instead of multiplying by circumference, you multiply by area. So times pi r squared. Theta over 360 times pi r squared. Or alternatively, there's proportions, in which you could take theta over 360, and that's equal to your sector area over your total area. Okay, so either way, it works the same. This is equal to your sector area. This involves your sector area and using proportions to solve. So with that, let's do a couple of examples with sector area here. First sector area example, or I guess we'll call it example 4 since that's what we're on overall for the day. So same idea, we've got a picture here. Okay, and a lot of times with sectors, they'll say like, what's the area of the shaded sector or something like that. So we'll say measure of angle ABC is equal to 57 degrees. BC is 6 inches. Find area of the shaded sector. Okay, so same idea here. We know angle ABC is 57 degrees. We know BC, this distance here, is a radius of 6 inches. So I know my sector area is going to be 57 over 360, since that's our formula here. There's our angle on top, times pi r squared. So pi times 6 squared. And I can plug this entire thing into a calculator, just like we did with arc length. So with that, grabbing our calculator, we're going to do 57 over 360. And then we're multiplying by pi times 6 squared. Type it in just like that. And we get 17.91. and that would be square inches here. Okay. Or we could be asked then, let's say this is part A, part B, what's the area of the non-shaded sector? All right. Well, if the shaded part had an angle of 57 degrees, the non-shaded part has an angle of 360 minus 57 degrees, which would be 303 degrees. So that's my new theta. And then we do the exact same thing as we did up here, except with 303 over 360 times pi times 6 squared. So all we would need to do in our calculator that's any different is replace the 57 with 303. And we get 95.19. Okay. So there's sector area. Any questions on that one? Any numbers we're not sure where they came from? Steps we're not sure how they work or anything like that? Okay. Then I'm going to let you finish up writing, and I'm going to post the homework, and we'll look at some of the problems together real quick. At least one of them anyway. Okay, so go ahead and open Google Classroom. Today's assignment is going to be in Big Ideas. You might have to refresh the page to see it show up. Here it is. Okay, practice 11.2. So we've got the first problem is an arc length problem, rounding to the nearest hundredth, just like we've been doing, 2 decimal places. The second one is a sector area problem. Let's start with the sector area one since you guys didn't get to do a U-try on there. Find the areas of the sectors formed by DFE. Round your answers to the nearest hundredth. So go ahead, try this one real quick. Find the area of the red sector and then the area of the blue sector. I'll give hints along the way. There's your formula. So if you start with the red sector and replace theta with 137, you're on the right track. And then R with 28. You get 937.31. And then for the blue sector, we're doing the same thing, except we have to go 360 minus 137. So if you did that, you're on the right track. And then just replacing the angle up here with 223 instead. And this one rounds to 1,525.70 because the 7 rounds the whole thing up. I don't know if it will take it without the 0 on there. Let's find out. Yep, it does. Okay. All right. So today's homework assignment has 15 total questions. And if you have questions, please stick around. Otherwise, you're free to go, and I will see you tomorrow. Sorry, class was a little bit longer than usual. We had a lot to do today.